Great, so welcome to this next lecture in computational solid mechanics. And today what I'm going to focus on now is first to just conclude our constitutive relation discussions and talk about planar problems, two-dimensional problems. So we've already done the nice full three-dimensional kind of situation, and now we want to see that we can also just simplify that full three-dimensional situation to essentially a plane stress and a plane strain problem, as well as there's a mixed problem in between. So essentially, if I have a body that is very, very thin and I put all the loading in the plane, then this thing can very easily contract. So it's like there's nothing holding that material back. And so with the plane stress problem, it's sort of a mathematical concept for if it was to be infinitely thin, but we typically use it just for when the bodies are fairly thin relative to the planar dimension. So you've got the dimensions of this body in the plane, and then you've got the out-of-plane dimension. That is relatively thin. And we know that the loading is in the plane, the response we're interested in is in the plane. And the material is such that if I were to give it an in-plane loading, that there is no asymmetry in the material that will cause it to wobble out of the plane, because then these things won't work. The other thing is we don't have any additional constraints. All the constraints are on the boundary. We don't have constraints that we put on the faces and stuff like that to constrain it. Like if I were to weld something here, a pin on there, then I wouldn't be able to do a plane stress kind of model. Okay, so that's essentially what it boils down. Make sure all your loading is in the plane. Make sure all your material properties are symmetrical such that the response remains in the plane. This is very important for composites. That can easily cause havoc if you have composites that are laminated in a specific way that causes an out-of-plane response. Then you have problems. And then essentially the loading, boundary conditions, all of those things are sort of in that plane, and the response you're interested in is to know what's going on in the plane. And what we'll see is that because this thing is so thin, if I pull on it, there'll be strain that will develop out of it. That's the only thing that's going to be non-zero here. So, and that's going to be the normal strain here. So any shear we're going to assume to be normal in this plane stress condition. But the only non-zero thing out of the plane is going to be strain. And that's why it's called plane stress, because in the plane is the only stress components that are non-zero. Okay. The other extreme is if you go towards this sort of infinitely thick body, and I've just given you sort of just an idea of a thick body, and I'm still looking at what is going on in this planar response. I'm still interested in what is going on in the planar response. And the loading and everything is still in this direction, yeah? But what happens now, as I pull on this in these directions, what happens is that this body can't really contract because there's a lot of mass here that's keeping the body from contracting. And so if that is the case, the strain out of the plane is zero. But because the strain is zero, it's holding the material back. It wants to contract if I were to pull on this, but it can't. And so there's a stress that will develop. And so the only non-zero thing out of the plane will be the stress component, but everything else will be zero. Okay, in terms of out of the plane. So there will be no kind of shear and no strains in this sort of that is connected with the z direction. And so what we see with this scenario again is this allows us just to model sort of very, very thick like dam walls and stuff like that in a way where we're still interested, and we make sure the loading and stuff is essentially in a way that is perpendicular to these planes, that we can make a slice out of it and make sure that this sort of planar responses are interesting. Okay, of what is of interest. And then the last thing is these mixed problems that we have. So there's mixed problems we can now essentially look at and say, okay, in a mixed problem we can try and model by a combination of these two. So that's one way of trying to do it. And the other way to tackle a mixed problem is just to do a full three-dimensional problem, because it's living in between the two. Okay, but these are your three typical scenarios when it comes to simplifications to the problem. Okay, so what I'm going to do is I'm going to stop the video so it's not too long. And then I'm going to do one video on plane stress, and I'm going to do one video where I'm going to just quickly drive plane strain. And I know it's stuff that you've done before, so just a quick recap, but it's important that we're all just on the same page, because we're going to be looking at a lot of the closed forms expressions that we're going to try and see if there are solutions to a problem are going to be sort of planar problem. Okay, thank you.